Hello friends, welcome to online lecture series. Today, we will continue our unit number first of Engineering Mathematics 2. In today's lecture, we will cover three different topics. Finding the integrating factor by rule number 3, 4 and 5. So, to find the solution of differentiable equation which is not exact. So, we will just summarize some basic rule number 1, rule number 2 and what is the basic idea behind rule number 1 and rule number 2 to convert the given non-exact differentiable equation into exact differentiable and finding its solution. We know that the differentiable equation is in the form of m dx plus n dy. So m into dx plus n into dy is equal to 0 is the first order, first degree differentiable equation. If this differentiable equation is homogeneous, then we can find its integrating factor by using the integrating factor formula, and that formula is, if the differentiable equation is homogeneous, then the integrating factor is 1 upon mx plus ny, where your mx plus ny, this is not equal to 0. If the given differentiable equation is not homogeneous differentiable equation, then the rule number 1 is not applicable to convert the non-exact differentiable equation into exact. For that, if the differentiable equation is in the form of this, means the function of your xy variables in which the coefficient of your dx is get multiplied by y, which is present in each and every terms. The similar way, x variable which is present in every term as a coefficient of your dy, then we can find the integrating factor by multiplying m with x and multiplying your n by y. Subtraction between them is not equal to 0, then we can find the integrating factor is 1 upon mx minus yn, where your mx minus ny, this subtraction never 0. If these particular two rules are not applicable to find the differentiable equation which is converting into exactness, means if your differentiable equation m dx n dy is not suppose homogeneous, and again this differentiable equation is not fitted in your rule number 2 also, it means your rule number 1 and rule number 2 both get failed to make the conversion of your differentiable equation into exactness. For that, we have to just go forward to rule number 3 to make the conversion of your differentiable equation into exact. For that, we have to just find the m and n from the given differentiable equation, differentiating your m with respect to y variable, differentiating n with respect to your x variable, and we have to make the subtraction between your derivative of your m with respect to y and the derivative of your n with respect to x. And this subtraction is get multiplied by 1 upon n. If we just make these calculations and we get only function of x as its final answer, then we can find the integrating factor of such a differentiable equation by finding the integration of your f of x with respect to x. Find integration of your f of x with respect to x. Whatever integration is formed, we have to just make as an exponential function index. So integrating factor of such a differentiable equation, which is not used to find its exactness by using rule number 1, rule number 2, and the integrating factor is e raised to integration of your f of x into dx is the integrating factor of your rule number 3. When this occurs, when subtraction of your derivative of your m and n with respect to y, x respectively is get divided by your n, and the final answer is your f of x, then we can find the integrating factor by using the formula. The integrating factor is equal to e raised to integration f of x dx. This is the integrating factor of rule number 3. Sometimes the rule number 3 also not applicable to find the exactness of your differentiable equation. For that, we have to just move forward for the rule number 3. Rule number 4. The rule number 4 tells us if the given differentiable equation is not a homogeneous, and these are the steps. Step number first, what? We have to write your m and n, differentiate your m with respect to y, and differentiate n with respect to x. Then we have to just find the subtraction of your m n with respect to your y, x, and divided by n. Before that, we have to check whether our given differentiable equation is exact or not. If the derivative of your m with respect to y is not exactly equal to derivative of your n with respect to x, it means the given differentiable equation is not exact. But the subtraction between the derivative of your m with respect to y and derivative of your n with respect to x is divided by n, we got only function of f of x. Then we can find the integrating factor is equal to e raised to integration of your f of x with dx. This is the integrating factor. And we know that after finding the integrating factor, the given differentiable equation can be multiplied by integrating factor. After multiplying the given differentiable equation by the integrating factor, we get the new differentiable equation, and that differentiable equation is exact. If the differentiable equation is exact, we know how to find a solution by using the rule number 1 of the solution of your exact differentiable equation. The rule is integration of your m dash with respect to x, we have to keep y as a constant. The second terms, we have to take the integration of your n dash with respect to y. The terms which does not containing x, we have to remove that one. And equal to c, the constant of integration defines the general solution of the given differentiable equation, which is solved by rule number 3. In a similar way, if the rule number 3 is not applicable, rule number 1 and 2 is also not applicable, means the rule number 1, rule number 2, and rule number 3, these 3 rules are not applicable to find the integrating factor of the given differentiable equation. Then we have to make them change. The small change is that we have to just divide the given subtraction of your m with respect to y and n with respect to x by minus m. Means if the rule number 3 is defined here, the derivative of your m with respect to y minus the derivative of your n with respect to x, which is divided by n, and that final answer is not equal to the only function of x variable, then the rule number 3 is not applicable. Rule number 3 is not applicable. So we have to make the small change. Instead of dividing this subtraction by n we have to divide the given subtraction by minus m. So dividing this particular subtraction by minus m, if the given subtraction is divided by your minus m, the answer is only the function of y variable, then we can find the integrating factor by taking the integration of your f of y with respect to y variable, and we have to just keep this particular integration as a exponential function index. The simple conversion is that if the subtraction between m and y, m and n with respect to y x, when divided by n, not the function of x variable, we have to move rule number 4. We have to divide same subtraction by minus m. If the final answer is the only variable of y, then we can find the integrating factor by using the integrating factor formula. Integrating factor is equal to e raised to integration f of x dx, which is used in rule number 3. And rule number 4, the small change, the variable x change with variable y. And the similar way we can find the solution of such a differentiable equation by using some suitable steps. First, we have to write your m and n, differentiate your m with respect to y, then differentiate your n with respect to again x. This differentiation, then we have to find the ratio subtraction. If the derivative of your m with respect to y is not exactly equal to the derivative of n with respect to x, the given differentiable equation is not exact. Is not exact, then we try for that. What we have to just make the subtraction of these both the derivatives and divide the subtraction by minus m. If we got only the function of y variable, then we can find its integrating factor by integrating this f of y with respect to y. We get the integrating factor. And lastly, we have to multiply the given differentiable equation by integrating factor. We get the new equation, and this new equation is 100% exact. So we can find its general solution by using the formula. Again, we use this formula several times. In this way, we can find the non-exact differentiable equation solution by using rule number 3 or rule number 4 according to the conditions. So we will see some example. Before example, just we have some shortcut tricks or shortcut to find the integrating factor of differentiable equation. If the derivative of m with respect to y and the derivative of n with respect to x, their subtraction is divided by n, and we got only function of f of x. Is the rule number 3 is applicable here. But what happens? Rule number 3 tells us the given subtractions divided by n gives only function of x variable. If the given function is in the form of minus a upon x, the given this particular function f of x is minus a upon x, then the integrating factor is directly written by 1 upon x raised to a, where a is any arbitrary constant. A is arbitrary constant. In the similar way, when the function f of x is in the form of a upon x, only the minus sign is not present, then the integrating factor is x raised to 4. X raised to a. In the similar way, if the function f of y is in the form of minus a upon y, the integrating factor is 1 upon y raised to 4. If the function f of y is in the form of a upon y, then we get the integrating factor y raised to a. These are some shortcuts to find the integrating factor of rule number 3 and rule number 4. We will see some examples that clears all the difficulties regarding to rule number 3 and rule number 4. We will just move forward for examples. Example number first, solve x raised to 4 e raised to x minus 2m xy square dx. plus 2mx square y dy is equal to 0. So we have to find the solution of this differentiable equation. For that, which particular rule is applicable, we have to identify. So first we have to check whether my given differentiable equation is exact or not. For that, we require m and n. So the given differentiable equation in the form of mdx plus ndy. Then what we have to do, we have to just find the derivative of your n with respect to x. So this derivative we have to find. After finding the derivative, we have to just check whether the both derivatives are equal or not. For that, we are just checking both the derivatives final solution. M in this example, m is x raised to 4 e raised to x minus 2m xy square, and n is nothing but your 2m x square y. So we have to differentiate this m and n with respect to y and x variable respectively. Then we are taking the derivative. The derivative of your m with respect to y, the first particular terms, that is a free from y. X raised to 4 e raised to x is the terms that does not containing m, that does not containing y. So it is the constant. It is constant. For the derivative of your constant is 0. The first derivative of this m with respect to y becomes 0, and the derivative of your y square is becomes 2y. The 2y is multiplied to minus 2mx. We got minus 4 times mxy. Similarly, we have to find the derivative of your n with respect to x variable. The derivative of your x square is 2x. Then we have to find the derivative of x square 2x. We got dy n upon dy x is equal to minus plus 4mxy. There is a small change. Both the derivatives are not equal. They are differ by their minus sign. So we said that the given differentiable equation is not exact. The differentiable equation is not exact, then we have to convert into exact. How? We have to just check whether the given differentiable equation is homogeneous. It is a fitted in rule number 2, or shall we apply for rule number 3 or rule number 4? From this given differentiable equation, we observe that the index of your x and y is differ. In the first term of your m, the index of your x is 4 and e raised to x is term is present, so it is not a homogeneous. And again, in the first term, y is not a multiplied, means not fitted in rule number 2 also. So we will just go for the rule number 3. We have to take the subtraction of both. Subtraction of your dy m upon dy y with dy n upon dy x is minus 8 times mx y. This is the subtraction, and we have to divide these particular terms by n or m. We have to identify. To identify this, the subtraction containing mx y and minus 8 is a multiplier of that terms. So we have to just check whether the m and n in which the single term is present. In n, the single term is present, it's a 2mx square y. This particular term means mxy is similar to your mx square y. So we have to divide the given subtraction by n. After dividing, we got the subtraction minus 4 upon x. It is the only function of x. So the integrating factor of such a differentiable equation is integration of your minus 4 upon x with respect to x, and that integration is nothing but the index of your exponential. So we will just take the integration. The integration of your minus x upon 4 is minus 4 log x. Minus 4 log x. Again, by the rule of your index log, minus 4 becomes the index of your x. So we get the new term, new particular step. That is a e whose power is log x raised to 4. Again, x raised to 4 is written as 1 upon x raised to 4. 1 upon x raised to 4. And again, we know that the e whose power is log x is nothing but x. So the index of your exponential function is log 1 upon x raised to 4. So the integrating factor is 1 upon x raised to 4. We have to multiply the given differentiable equation by 1 upon x raised to 4. That is my integrating factor. Then after multiplying, we get this, the given differentiable equation. We multiplying the given differentiable equation by integrating factor. Then next step, we have to multiply each and every particular terms by 1 upon x raised to 4. We are making the separate calculations. The first x raised to 4 e raised to x. These particular terms get multiplied by 1 upon x raised to 4. It becomes x raised to 4 e raised to x upon x raised to 4. In 2mx y raised square is get multiplied by 1 upon x raised to 4 becomes 2mx y square upon x raised to 4 into dx. And similar way this. Again, we have to just make the cancellation of x raised to 4, x raised to 4. Again, the power of x is 1 and power of x is 4 in your numerator and denominator respectively. We have to make the cancellation. Again, x square is cancelled with your x square, which is present in your numerator and denominator respectively. So, we got a new particular terms. That is a e raised to x minus 2my square upon x cube into dx. Plus 2my upon x square dy is equal to 0, which is the differentiable equation in the form of m dash dx plus n dash dy. And we know that after multiplying the given differentiable equation by integrating factor, it becomes exact. If this differentiable equation is exact, we can find its solution directly. How to find the solution? We have to use the rule number 1 formula. Given differentiable equation is exact, we have to find its solution. And can we find the m dash e raised to x minus 2my square upon x cube dx plus the terms which does not containing x. We have to just take here the term which does not containing x but in n, the x square is present, so we have to neglect the term that terms. The derivative of your e raised to x is e raised to x, and the derivative of your x raised to minus 3 is x raised to minus 2 divided by minus 3 plus 1. Then making the simple calculations, we got the solution of your differentiable equation, that is e raised to x minus 2my square x raised to minus 2 divided by minus 2. It's minus 2 and this minus n becomes positive. So did 2 get cancelled. We get a final solution e raised to x plus my square x square is equal to c. This is the final solution of our differentiable equation, which is not exact. So we will move on next one. So we have to solve this differentiable equation. Solve y 2x y plus e raised to x dx is equal to e raised to x dy. The given differentiable equation is not in the mdx plus ndy form, because the differentiable equation can be written in the mdx plus ndy form. We have to shift e raised to x dy to your left hand side, it becomes negative and is equal to 0. Here m is equal to y 2x y e raised to x into y. This y is get multiplied to this, then we get 2x y square plus y e raised to x dx. And e raised to x is nothing but your value n with minus sign. Differentiating this, we have to differentiate m with respect to y. So y square derivative is 2y and 2x becomes 4xy. Derivative of y is 1. We got e raised to x. Derivative of e raised to minus e raised to x is e raised to x itself with minus n as it is. When we observe this, these two are not similar. Means the given differentiable equation is not exact. So dy m upon dy y not equal to dy n upon dy x. the differentiable equation is not homogeneous, not exact, not fit in rule number 2, then we have to just go for the rule number 3. Rule number 3 and rule number 4. The subtraction is of these two derivatives are 4xy plus 2e raised to x. We have to just identify which particular terms, either m or n, is suitable to make the dividation. When we observe here, the subtraction is 4xy plus 2e raised to x is here. Which particular terms is divided? Here we can make this dividation. Then we have to divide by minus m. We have to divide by minus m. Minus m is what? This y times 2x e raised to x. We have to multiply this. Again, when we take 2 common in your numerator, okay, I will just make one extra step here. When we make 2 common, the numerator and denominator containing same ratio, same particular terms, that ratio get cancelled. Then finally we got minus 2 minus 2 upon y is the solution. Then when we observe this, minus 2 upon y is the only function of x. When we use the shortcut method to find the integrating factor becomes 1 upon y square. We will see that how to find the integrating factor. This is the very easy. We already saw the rules. The integrating factor is the integration of minus 2 upon y, not dx, it is a dy. And it is the power of your exponential function. So integration of minus 2 upon y is minus 2 times log y. Again, the index rule of your logarithm, the log of y raised to minus 2. Again, this y raised to minus 2 can be written as 1 upon y square. And we know that e raised to log x or e raised to log is nothing but the value of your logarithm. That is a 1 upon y square is my integrating factor. Multiplying these particular terms by integrating factor, we get a solution. A new differentiable equation, and we can find its solution. We already done this. A differentiable equation is multiplied by 1 upon y square. 1 upon y square is multiplied to y in bracket 2x y plus e raised to x dx. Again, e raised to x multiplied by y square. Then we have to find its solution. This differentiable equation is exact. The y square y get cancelled. We get 2x. And again, this y square index becomes y 2y y square. Then y square get cancelled. We get 2x. And e raised to x upon y. This is exact differentiable equation. We have to find its solution. And for the solution, we have to integrate your m with respect to x, and we have to integrate your n with respect to y. N does not containing x. So here the n in which exponential function is present, so we have to remove that particular terms. We have to find the integration of 2x plus e raised to x upon y with respect to x only. So this is the terms which occurs. We have to find the integration. Then the integration of your 2x is 2x square upon 2. And integration of your e raised to x is e raised to x itself. And when we make the simplification of this, we get a final solution like this. As 2 get cancelled, we get only the x square. The x square is my solution. E raised to x upon y plus c. Somebody can be express this solution in the way by dividing this y is get multiplied to each and every terms. We get only the e raised to x. And again, y is multiplied here. This is nothing but only e whose power is x. This is the solution of the D1 differentiable equation by using rule number 4. In similar way, we can find the solution of another can find the solution of another differentiable equations by using rule number 1, 2, 3, 4, depends on the differentiable equations type. We will just move forward for the rule number 5th. If the differentiable equation is not make the converted into exact by using rule number 1, 2, 3, and 4. Means the rule number 1, 2, 3, 4 are get failed, and the differentiable equation mdx plus ndy can be expressed in the form of a raised to x raised to a, y raised to b, my tx plus nx dy plus a1 x raised to a1, y raised to b1 in bracket m1 y dx n1 x dy. Then such a differentiable equation is not used to solve by using rule number 1, rule number 2, rule number 3, rule number 4. Is all rule number 1 to 4 get failed. Rule number 5 is the universal method to find the integration factor of all differentiable equations. So a, b, a1, b1, m, m1, n, n1 are the constants. These are the some real numbers or some numbers which are present in your differentiable equation. So for this differentiable equation, we have to find the integrating factor, and the integrating factor can be solved by just if checking the condition. If your m into n1 minus n into m1, this particular subtraction is not equal to 0. If this is true, then we have to assume the integrating factor is equal to x raised to h, y raised to k. Only this is the assumption of your integrating factor, and we have to find h and k by solving the simultaneous equation. This is the way in which we can find the integrating factor if the rule number 1 to rule number 4 are get failed. So x raised to h, y raised to k are the integrating factor of our differentiable equation. Then the steps involved in this, we have to write m and n. Then we have to just take the derivative of your mn with respect to y and x. The next step, we have to just check whether the given differentiable equation is exact or not. If not exact, then we have to try for the rule number 1, 2, 3, 4. The rule number 1, 2, 3, 4 are failed, and the equation can be expressed in this particular form. Then we have to assume x raised to h and y raised to k as an integrating factor. Then multiplying this by integrating factor to our differentiable equation, we got a new differential equation, that is a m dash. Differentiating m dash with respect to y and n dash with respect to x, we get derivative of m dash with respect to y, dou y m dash upon dou y, and this derivative is exactly equal to dou y n dash upon dou x. When we equate these two, because the differentiable equation becomes exact, if the differentiable equation becomes exact, then its necessary sufficient condition tell us the derivative of your m dash with respect to y is exactly equal to the derivative of your n dash with respect to x. From this, we can find the value for h and k. Then next, we have to put h and k in the assuming integrating factor. We get the integrating factor value, multiplying the given differentiable equation by integrating factor, and this differentiable equation becomes exact, and finally we can find the solution by using the solution of differentiable equation. The integrating your m dash with respect to x, keeping y constant, and the terms which does not contain x, we have to integrate with respect to y, is equal to the constant of integration is present. We will see an example. The example will tell all the idea regarding to the rule number. The example is given here. Example is solve y square plus 2y x square dx plus 2x cube minus xy dy is equal to 0. The given differentiable equation is m dx plus n dy. So we have to just find the derivative of your m with respect to y and the derivative of your n with respect to x. The derivative of your m with respect to y is 2y plus 2x square, and the derivative of your n with respect to x is 6x square minus 1. We observe that these two derivatives are not same. Then the given differentiable equation is not exact. The differentiable equation is not exact, then we have to just make into exact by finding the integrating factor. When we observe carefully the differentiable equation, the index of your y is 2 and index of your second term is y is 1 and index of x is 2. So m is not homogeneous. Also in n, two terms whose indexes are differ. So n is not also homogeneous. Means the given differentiable equation is not homogeneous, as well as it not is fitted into rule number second also. And rule number 3 and rule number 4 both are get failed to find the integrating factor of such a differentiable equation. So we have to make the conversion. We have to just multiply this dx to the whole its coefficient and dy to its whole coefficients. So the equation is becomes y square dx plus 2yx square dx plus 2x cube dy minus xy dy. So we have to combine x dx and dy together. So we are representing this the y square dx and x dy. So we have to just make the combination of dx dy such that the index of variable y goes on decreasing. In the second, the index of your x goes on increasing. In the first two steps, the coefficient of your dx is y square and the coefficient of your dy is become x y and the index of y is 1. Then term number third and fourth, the index of your x goes on increasing, that is x square and x cube. So we have to take y common from your first two terms and x square common from your last two terms. So the example becomes multiply to y dx minus x dy plus x square 2y dx plus 2x dy. So the example is in the rule number 5. So we have to assume the integrating factor x raised to h and y raised to the given differentiable equation in the form. Here when we observe the value of your a is 0, value of your b is 2, m is 1 and so on. So we have to assume the integrating factor is x raised to h, y raised to k, their product. After assuming the integrating factor, we have to multiply this particular differentiable equation by the integrating factor. So we get the new particular differentiable equation and that equation becomes exact. After multiplying the differentiable equation by your integrating factor, we get the equation of in the form of h and k. So this is the equation after multiplying the integrating factor. So we multiplied one by one. So the equation becomes x whose power is h into y whose power is k plus 2, 2x whose power is h plus 2, y whose power is k plus 1 and dx. The next step, 2x whose power is h by 3 multiplied y raised to k minus x whose power is k plus 1 and y whose power is k plus 1 and x whose power is h plus 1 is equal to 0. After multiplying this differentiable equation, the differentiable equation becomes exact. It means the value for m dash is equal to your first bracket and value for n dash is your second bracket. When we just make the comparison between these two equations, that is m dx plus n dy, then m dash is equal to your first bracket and n dash equal to your second bracket. So we get a value for m dash we have to just make the derivative of your m dash with respect to y. And that derivative is k plus 2, x raised to h remains constant, and index of your y reduced by 1, it becomes k plus 1. Similarly, the index of your y becomes k, and the index of your h remains k, x remains h plus 2, and 2 is the coefficient. Similarly, we can find the derivative of your n dash with respect to x. So we got the new equation, that's a del y n dash upon del y x is, after differentiating, 2 times h plus 3, x raised to h plus 2, y raised to k, minus h plus 1, x raised to h, y raised to k plus 1. After multiplying the differentiable equation by integrating factor, the differentiable equation becomes exact. It means the del y m dash upon y is equal to del y n dash upon del y x. This is the condition of your exact. Means we have to compare both the equations. Then we are comparing this equation, and we have to just make the comparison between the coefficient of your same index. The x raised to h, y raised to k plus 1, whose coefficient is k plus 2, and the right hand side, the index of your x is h and y index is k plus 1, whose coefficient is minus h plus 1. So we have to compare the like indices coefficient. We got two equations. The equation number first is k plus h equal to minus 3, and second equation is k minus h equal to 2. When we solve these two equations, we got the value of your h and value of your k. So we have to just finding the value of your h and k by solving the simultaneous equation. The h equal to minus 5 by 2 and k equal to minus 1 by 2, putting the value of your h and k in this equation. The equation becomes this equation number A. So we have to replace the value of your h and value of your k. We have to just put the value. The differentiable equation is exact, because my multiplying factor, that is the integrating factor, is x raised to minus 5 by 2 and y raised to minus 1 by 2. After multiplying, the equation becomes x raised to minus 5 by 2, y raised to minus 1 by 2 plus 2, 2x minus 2x whose index is minus 5 by 2 plus 2, y whose index is minus 1 by 2 plus 1 into dx, and the index of your x is minus 5 upon 2 plus 3, index of y becomes minus 1 by 2, index of x becomes minus 5 by 2 plus 1, and index of your y becomes minus 1 by 2 plus 2. Means after replacing your h and k in the given equation, we got the new differentiable equation with different power. That is defined here. So according to condition of your exactness, this differentiable becomes exact. Finding the directly solution of the differentiable equation by using the rule number first of finding the solutions condition. So m dash is your first bracket. N dash, we have to just select the terms which is not containing x. But this example does not containing any terms which is free from x. So n dash, in that all terms are 0. X terms is 0. We have to find the integration of this. The integration of your x raised to minus 5 by 2 is, we have to add 1 in its index, and the same particular index is get divided to your x. So we get this particular. The y raised to 3 by 2 is by constant, it remains as it is. The index of your x in which we have to add 1 by the integration rule, the integration of your x raised to n dx is in x raised to n plus 1 upon n plus 1. According to that, we are finding the integration and making the calculations. Minus 5 by 2 plus 1 and minus 1 by 2 plus 1, we got this. And lastly, we are making the rearrangement of your differentiable equation, and we get a final solution is this 2 by 3 and this 1 by 2 multiplied to this 2 becomes 4, This 3 by 2 multiplied to your this equation becomes 2 by 3. And lastly, making the arrangement of your equation, multiplying the whole equation by 3 by 2, we get the final solution. In this way, we can find the solution of your differentiable equation if the rule number 1, 2, 3, 4 are get. Okay, we will stop here. Thank you.